Hey, welcome to yet another lesson. This lesson is a very basic lesson, an introductory lesson on the atmosphere. Atmosphere is the very medium in which all aviation activity takes place. So it's very important for us to understand the nature and the behavior of atmosphere so that we can appreciate the aircraft performance at different levels and different stages, and there are several other phenomena which take place. So it's very important for us to understand what atmosphere is all about, and therefore this class is being pitched in accordingly. We already saw the picture of the solar system. First, I thought I will just give a brief introduction to our Earth and the solar system. Just a few brief facts. It's called the blue planet for its own reason. It looks blue in color because of the water spread when seen from far away. It's the third planet from the sun and the fifth largest planet. And it has got 30% of land coverage, and 70%, remaining 70% is the water or oceanic coverage. It's for this reason it is called the blue planet, and it looks blue in color. Let's learn more about the atmosphere. Based on the properties of the air and across which changes as we go from the surface of the earth to top, there is a gradual change and on several parameters. So the entire atmospheric layer is divided into different layers depending on its properties. So to start with, the lowermost layer is called the troposphere. It varies from 9 kilometer at poles to 17 kilometers at equator. Why? Because that's the homogeneous character of that particular layer. That means it has similar properties up to 9 kilometers over poles and 17 kilometers over the equator. Most important to note that most of the moisture vapor is contained in this troposphere, and needless to say that if because of the moisture, it gives rise to weather phenomena, which we are going to learn in a great detail in our meteorology lessons. The boundary of troposphere is called the tropopause. It's just a small layer where the transition from uh, one set of property another set of property will take place. The next higher level is called the stratosphere, which extends from 12 to 50 kilometers. Next layer above which rests the mesosphere from 50 to 80 kilometers, and the thermosphere 80 to 700 kilometers, and of course the exosphere is 700 to 10,000 kilometers. Okay, I thought I'll share some interesting data about the atmosphere. Weight of the atmosphere is about 1 millionth as that of the earth, and an air column of 1 square meter of air weighs about 9,800 kilograms. The mass of the Earth's atmosphere is distributed in the following manner: 50% is below 5.6 kilometers, that is below 18,000 feet. That means most of the atmosphere is distributed below 18,000 feet, and 90% is below 52,000 feet, and 99 point, that is almost about 100% is below 100 kilometers. So the earlier layers which we were talking about, why we are talking about, it's for maybe a different reason which we will learn. The Kármán line marks the beginning of the space where that's where that means above 100 kilometers, that means 3,30,000 feet. If one were to cross, it is called the Kármán line. If one were to cross this, then it is called the space travel, or that's how space travel is being defined. And these people, these human travelers are considered astronauts. Let's see the composition of the atmosphere per se. As I have shown in this graph, the top figure is by volume, and the bottom figure, which is given a light green color, is by weight. So let's go over. Nitrogen is about 78.08% is occupied by nitrogen, and oxygen occupies 20.94. So nitrogen, oxygen almost constitute 98-99% of the atmosphere. Then argon is about 0.93. Carbon dioxide is very small, and there are many more other small traces of gases which I have shown, which I will go through also. Hydrogen, neon, helium, krypton, xenon, ozone, and radon. These are the other gases which constitute the atmosphere. So, as I explained to you earlier, this division of layers in the atmosphere is based on the set of characters, or the set of behavior properties which is found in uniform. So I will just go over them. I will just go over one such important property of temperature. Basically, the lapse rate, that the rate at which the temperature drops as we go up in the atmosphere, is approximately 1.98 degree centigrade per 1,000 feet. That's it. That's considered as the uniform rate. Let's go some more in detail. So, from the surface, the troposphere is the lapse rate is what I told you, and as it keeps going, it reaches the lowest temperature of minus 56.5 degrees centigrade at 36,090 feet, and thereafter it remains steady for some time. I want you to keep following the graph as we go through the explanation. And this place where it reaches a static figure of minus 56.5 marks the tropopause. Thereafter, it's the beginning of stratosphere. The stratosphere temperature rises, but still remains below freezing level, that is below 0 degrees centigrade. So here you can see it's approximately about 45 to 50 kilometers. It still remains below freezing temperatures. Thereafter is the mesosphere. In the mesosphere, the temperatures can reach up to minus 120 degrees centigrade. Can reach up to 120 degrees. Yeah, I've shown only up to minus 90 degrees centigrade. And thereafter, by the time it reaches 100 kilometers, the temperature starts rising fairly rapidly, and it can reach temperatures up to 2000 degree centigrade. Now that we are here, I want to explain some more. The ozone layer is a very important layer. It is located in the lower portions of the stratosphere. It performs a very important function of blocking harmful ultraviolet radiation from the sun, which can be very harmful for human beings. Anyway, there is another layer, not a distinct layer. It is we are going to learn about this layer much in detail in our avionics class. It's called the ionosphere. It because of the sun effect, the electrons of the atoms are split up, and there's a lot of ionization which take place of the atmosphere. It's basically a daytime activity, and it happens between mesosphere and thermosphere, and it has got its own characteristics, which we will learn it in detail in our avionics class. Then there are other layers, homosphere, heterosphere, and for they are used in different context and for different reasons, which it's just for information sake. I thought I will put it here. Let's go through as to how the atmospheric pressure varies in the atmosphere. Atmospheric pressure drops gradually, and we can consider that it is dropping at a uniform rate. However, since density also drops, the rate of drop of pressure declines as altitude increases. Now, this rate of drop can be considered as 30 feet per millibar. That means that's the scale in which atmospheric pressure is measured. It's either millibars or hectopascals, both are same. It is known as hectopascals nowadays. Now, I have tried to show uh, at different heights how much is the pressure difference. Like at 5,000 feet, the pressure is 12.22. The difference between 5,000 and 10,000 feet, that is 12.22 and 10.11, that's 2.11. Whereas from 10,000 to 15,000 feet, uh, you will notice that it's a different figure, and so on as we keep going up. You see the difference between 35,000 to 40,000 feet. That's about 2.72 to 3.46. That's about it. That is uh, 28 plus 0.46. That if you can work it out. So it's much less. That's the way the pressure difference varies. Okay, let's talk about the density of the atmosphere, which is very important to understand. Provided the temperature remains constant, density is proportional to the pressure. This is according to the gas laws. However, since density also drops, the rate of drop declines as altitude increases. This is what we have earlier discussed. Density varies inversely with the temperature provided pressure remains constant. This is also one of the gas laws. So, the effect of pressure on density has a dominating effect than that of the temperature, which are in opposite to each other. That's what I want you to understand. More about density. Humidity, increased humidity leads to drop in density. And one important parameter which you will need to understand that you will keep coming across is the density altitude, on which all the performance of the aircraft is dependent on. So eventually we are going to be working in terms of density altitude. So earlier we talked about the pressure correction, that is from the standard pressure, if there was a deviation how much, and here 120 feet per degree centigrade is a good approximation to calculate the density altitude. That means a deviation from the standard temperature uh, 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 is we can consider 120 feet per degree centigrade as a standard correction. Since several parameters keep varying according to several phenomena throughout the day, and so it's you have to have a uniform base scale on which you start the you keep that as a base scale for measurements, and we have decided that there is a scale to decide to determine the international standard atmosphere. What are they? They are as shown: standard sea level temperature of 15 degrees centigrade and pressure of 1013.2 hectopascals, standard density of 1.225 kilograms, and lapse rate at 1.98 degree per 1000 feet. These are the parameters considered standard at international atmosphere. From here, any deviations will be measured. Okay, as usual, let us go through a numerical example to clarify the concept more clearly. What is the density altitude at 15,000 feet if the local QNH is 1009 hectopascals and the temperature is minus 10 degrees centigrade? Okay, let's see how much is the ISA deviation. Okay, to be for the sake of this example, we will take it as 2 degrees per centigrade, 2 degrees centigrade per 1000 feet. So, at 15,000 feet, the standard temperature should have been the deviation from standard temperature would be 30 degrees. That is 15 into 2, 30 degrees. That is from sea level temperature. If the standard temperature which we have defined as 15 degree and lapse rate is 2 degrees centigrade per 1000 feet. Now the standard temperature at this altitude would have been minus 15 degrees centigrade. However, the current temperature is minus 10. Therefore, the deviation is plus 5 degrees centigrade. Similarly, uh, the standard pressure is deviation by 4 hectopascals. So, as we learnt, 30 feet for every hectopascals, that is 4 into 30 is 120 feet, and temperature deviation is 120 feet per degree centigrade, so into 5 is 600 feet. Therefore its pressure is lower, so the altitude is going to be higher, temperature is higher, therefore the altitude once again has to be higher. Therefore 15,000 feet plus 120 plus 600 is 15,720 feet. That's going to be the density altitude. The important property of the atmosphere which I want you all to understand, that is the viscosity. Viscosity is equivalent of what is a friction for solids. That means when one solid is kept over the layer of the other solid, uh, there is a force when you try to move one solid, which is we called friction. Similarly, the air molecules tend to stick to each other while flowing. So this tendency is called viscosity. So it's same as friction for solids, viscosity for air. But we need to understand, we know that for viscosity we have learnt we understand for liquids, and we also understand that viscosity is reduces with increase in temperature for liquids. However, I want you to notice here, for air viscosity increases with temperature. So we are going to talk in terms of coefficient of absolute viscosity. because viscosity per se has got doesn't have much of meaning. Why? Because it keeps varying depending on temperature and several other conditions. So we will uh, just to explain this viscosity some more. It is the proportion of shearing stress to velocity gradient. I want you to have a look at this picture. See, each arrow represents one layer of atmosphere, and the reverse arrow, which I have big arrow, which I have shown in red, is the tendency of the lower layers to stick to each other and retard in the opposite direction of the air flow. This tendency is called viscosity, and the measure of it is in shearing stress. And when compared to the velocity gradient, that means the you see the upper layer where I put v1, that layer of air travels it at some v1, and because of the frictional or viscosity effects, the layers below tend to retard in the opposite direction and drop to a lower figure, which is what we call velocity gradient. So this is called the coefficient of viscosity. uh, since it is again, there is another ratio which we would be more interested in, is called the kinematic viscosity. That is the coefficient of absolute viscosity when upon the density of the air is called the kinematic viscosity. The details of it we are going to discuss in yet another class. So at this point, it's enough if you understand the definition per se. Okay, we discussed several parameters, and I want you all to understand these parameters keep varying, as I told you, uh, during the day, during the season to season, and several other phenomena. There could be sudden variations and things like that. So, the absolute figure itself has not it doesn't convey much meaning. So it's most of the times it is compared with the standard level parameters, standard parameters, so that we know how much which means, what I mean to say, a temperature of 10 degrees at sea level is not same as temperature of 10 degrees at 3000 feet. Why? Because uh, at sea level the standard temperature is 15 degrees centigrade, and a temperature of 10 will mean uh, a deviation of just 5 degrees from the standard. Whereas at 3000 feet, if the temperature was 10 degrees, then the standard temperature itself will be different, -6, that is 9 degrees. 9 to 10, the deviation is just about 1 degree. So, so we always talk in terms of ratios, be it temperatures, pressure ratio. The current value is always compared with the standard figure, so that it conveys a much better meaning. Okay, this is a lesson in aerodynamics. So, what is the link between atmosphere and aerodynamics? We want to understand how airplanes behave in the atmosphere, and that's why we studied the atmosphere and its characteristics. So, for all our aerodynamic theories, we have a basic assumption that air is an ideal fluid. That is, what is an ideal fluid? An ideal fluid is one which is incompressible and non-viscous. So that's what is we call ideal fluid. But we know the fundamental fact that air is viscous and it is compressible as well. But for all practical purposes of the subsonic study of aerodynamics, that is up to fairly good degree of airflow speeds, it behaves like an incompressible and non-viscous fluid. That is, the air behaves like an ideal fluid. So we are able to understand the nature of aerodynamic characteristics and behavior of several planforms by assuming that air is an ideal fluid. So, at least for the initial parts of our study of aerodynamics, it is good enough to understand that air is an ideal fluid, and thereafter, any deviations from there can be studied in detail. But it is important to understand that air is compressible and it is viscous. Okay, we come to the end of the lesson. There's a lots to study about atmosphere, but I've just taken the bare minimum. And what is required for us for our study and for our understanding is what has been covered. So there are several other resources, and one, if one is interested, we can you can go through and improve your knowledge. But I hope you found this lesson interesting, and please feel free to offer your comments on the email ID given below. And please follow the website and my YouTube channel for further lessons and several other lessons which you will find useful. Thank you very much for having gone through